Hello everyone, I am Rakshita studying Electronics and Communication Engineering in Sri Venkateswara College of Engineering, Bangalore. Today we are going to discuss on a topic periodic functions in a Fourier series. Let's move forward to the introduction part. Introduction to periodic function in a Fourier series. Periodic functions are the functions that repeat their values at regular intervals. Fourier series is a mathematical representation of a periodic functions using a sum of a sine and a cosine functions. Fourier series is widely used in various fields such as signal processing, image compression, and audio synthesis. Formula for the Fourier series is given as g of t equal to a naught plus summation n equal to 1 to infinity a n cos n omega naught into x plus summation n equal to 1 to infinity b n sin n omega naught into x. Let's move forward to the next slide. Basic concepts of a Fourier series. A periodic function f of x with a period t can be represented as a infinite sum of sine and a cosine functions. The Fourier series of f of x is given by f of x equal to a naught by 2 plus summation a n cos n omega naught into x plus bn. Fourier series coefficient of a square waves. You can see it on the screen. Let's move forward to the next slide. Fourier series coefficients. The term a naught by 2 represents the DC component of the periodic function. The coefficient an and bn represents the amplitude of the sine and the cosine functions respectively. The higher the value of n, the more oscillations are captured in the Fourier series representation. You can see some of the formulas on the screen. F of x equal to 1 by 2 a naught plus summation n equal to 1 to infinity a n cos nx plus summation n equal to 1 to infinity b n sin nx, where a naught equal to 1 by pi interval minus pi to pi f of x into dx, a n equal to 1 by pi interval minus pi to pi f of x cos nx into dx, bn equal to 1 by pi interval minus pi to pi f of x sin nx into dx, where n equal to 1 comma 2 comma 3 and so on. Convergence of Fourier series. The Fourier series representation of a periodic function converges to the original function under certain conditions. If the periodic function is piecewise continuous and has a finite number of discontinuities within a period, its Fourier series converges to the function at a point of continuity. At points of discontinuity, the Fourier series converges to the average of the left and right limits of the function. Fourier series periodic functions. F of t equal to a naught by 2 plus summation n equal to 1 to infinity a n cos n omega t plus b n sin n omega t, or f of t equal to 1 by 2 a naught plus a1 cos omega t plus a2 cos 2 omega t and so on, plus b1 sin omega t plus b2 sin 2 omega t and so on. For the function f of t, where omega equal to 2 pi by t, the coefficients are calculated by an equal to 2 by t interval 0 to t f of t cos n omega t into dt for n equal to 0, 1, 2, 3 and so on. Bn equal to 2 by t interval 0 to t f of t sin n omega t into dt for n equal to 1, 2, 3 and so on. Let's move forward to the next slide. Even and odd functions. An even function is a symmetric about the y-axis, that is f of x equal to f of minus x. The Fourier series of an even function contains only cosine terms. An odd function is a symmetric about the origin, that is f of x equal to minus f of minus x. The Fourier series of an odd function contains only sine terms. For a general periodic functions, the Fourier series can have a combination of both sine and cosine terms. Let's move forward to the next slide. Harmonic analysis. Harmonic analysis is the process of decomposing a periodic function into its constituent sine and cosine functions. The Fourier coefficients provide information about the amplitudes and the frequencies of the individual harmonics. By analyzing the Fourier coefficients, one can determine the dominant frequencies present in the periodic function. Let's move forward to the next slide. Periodic extension. The Fourier series representation can be extended to non-periodic functions by periodic extension. The non-periodic function is extended periodically over a larger interval and its Fourier series is calculated over the interval. This technique allows us to analyze non-periodic signals using Fourier series concepts. Applications of Fourier series. Fourier series is widely used in audio signal processing for compression and synthesis of sound. It is used in image compression algorithms such as JPEG to represent images in frequency domain. Fourier series plays a crucial role in analyzing and processing signals in various fields like telecommunications, control systems, and physics. You can see the original signal, Fourier spectrum of a signal, close up of a lower end of the Fourier spectrum, filtered signal. Let's move forward to the next slide. Fast Fourier transform. The fast Fourier transform FFT is an efficient algorithm for calculating the Fourier series coefficients. It reduces the computational complexity of Fourier series calculations from O n squared to O n log n, where n is the number of samples. The FFT algorithm revolutionized signal processing and made real-time analysis of large data sets possible. Let's move forward to the next slide. Limitations of Fourier series. Fourier series assumes that the periodic function is both continuous and differentiable. It may not accurately represent functions with abrupt changes or discontinuities. The convergence of the Fourier series can be affected by the presence of high frequency components or a noise in a signal. You can see the Fourier series synthesis. F of t equal to a naught by 2, that is a DC part, plus summation n equal to 1 to n a n cos 2 pi n t by caps t, even part, plus summation n equal to 1 to n bn sin 2 pi n t by caps t, that is a odd part. T is the period of all the above signals. Let omega naught equal to 2 pi by t. F of t equal to a naught by 2 plus summation n equal to 1 to n a n cos n omega naught into t plus summation n equal to 1 to n bn sin n omega naught into t. Relationship with the complex numbers. Fourier series can be expressed in the terms of complex numbers using Elew's formula. The real part of the complex Fourier series represents the cosine terms and the imaginary part represents the sine term. The complex representation simplifies the calculations and provides a concise form of a Fourier series. Gibbs phenomenon. Gibbs phenomenon refers to the overshoot and the oscillations observed at the edges of the Fourier series approximation. It occurs due to the inability of the Fourier series to accurately represent sharp transitions in a function. Although the overshoot is unavoidable, the magnitude of the overshoot can be reduced by adding more terms to the series. Practical considerations. In practical application, truncation of a Fourier series is often necessary due to computational limitations or desired accuracy. Truncation refers to using finite number of terms in a Fourier series approximation. The accuracy of the approximation increases as more terms are included, but at the cost of increased computational complexity. Example of a Fourier series. Let us consider an example of a periodic square wave function. The Fourier series of the square wave consists of odd harmonics with decreasing amplitudes. By including more terms in the series, we can improve the accuracy of the square wave approximation. Thank you for watching my video. Please like, share and subscribe my channel.